Welcome to another one of my SAT mathematics videos. This video is going to be especially long. We're covering the second part of geometry, namely quadrilateral circles and 3D shapes. Before that, some general facts. The sum of interior angles in any polygon is n minus 2 into 180, where n is the number of sides. So if it's a quadrilateral, the shape has 4 sides. 4 minus 2 is 2. 2 into 180 is 360 degrees. Therefore, the sum of the angles inside a quadrilateral is 360. Similarly, you can use the same formula for any polygon. I just recommend you practice using it on these polygons, and these are the answers. And let's just look at another quick example from here. The octagon, it has 8 sides. 8 minus 2 is 6. 6 into 180 is 1080. Therefore, which corresponds with the sum of the interior angles of an octagon, and that's just to show it works. The sum of the exterior angles of a polygon is always 360 degrees. So they might give you 5, ask you for the 6th one. They might label each angle as an algebraic term and an algebraic expression, and they'll ask you to find the value of x, and therefore you just need to add all of them equated to 360. And what an exterior angle basically is if you extend each of these sides, the angle it makes with another side is the exterior angle. And for any polygon, the sum of these exterior angles are always 360 degrees, is always 360 degrees. And now let's actually go to quadrilaterals, which is one of the main segments in this video. The first shape that the SAT requires you to know properties about is a parallelogram. So the opposite sides are parallel and congruent. So this and this are parallel and at the same time equal in length. The same applies for these sides, which are also opposite to each other. The opposite angles are equal, so this and this is also equal. Adjacent angles, so this and this, or this and this, or this and this, add up to 180 degrees. If just think why is this? Because think about it, they're just corresponding angles. You have two parallel sides being cut by a transversal. Therefore, the corresponding angles adding to 180 degrees makes these adjacent angles supplementary. The diagonals bisect each other, which means I divide them into equal halves. So this and this is equal to this, and this is equal to this. And the diagonal splits the parallelogram into two equal triangles, two congruent triangles. So this is congruent to this. Area is length into height. Height is perpendicular height over here. A rectangle is a special type of parallelogram, which means it has all these properties, but all its angles are additionally 90 degrees, and its diagonals are congruent. They're equal together. In a parallelogram, the diagonals are not congruent, and area is length into width. Now a square is a special type of rectangle. What this means is it has all these properties of a parallelogram. It also has all these properties of a rectangle with a few additional ones. In a square, all these sides must be equal. The diagonals are perpendicular to each other, which means they make 90-degree angles with each other, and they bisect their angles, which means this is 45, this is 45, this is 45, this is 45, because they're bisecting the 90-degree angle. And the area over here is a square, where a is the side length, right? You really need to know everything on the slide. Over here, you only really need to know the isosceles trapezium, by which I mean questions are asked most frequently about those 4 quadrilaterals, but I've put 2 additional ones just to be safe. Rhombus, it's a special type of parallelogram in which all sides are equal. See, diagonals bisect the angles. Opposite angles and sides are equal, just like in a parallelogram. Opposite angles equal, opposite sides equal. Opposite sides are also parallel, like in a parallelogram. The adjacent angles are also supplementary, so they add up to 180, like in a parallelogram. And the area, however, is half into the length of one diagonal into the length of the second diagonal. A kite is shaped like a kite, and they have 2 pairs of sides that are equal in length. So this and this are equal in length, and this are equal in length. They have 1 pair of equal angles. This and this are equal, not this and this. That's because this triangle and this triangle are congruent, but this triangle and this triangle are not congruent. Only one diagonal is bisected when they cut, so only this diagonal splits, D2 splits D1 into equal halves, but D1 does not do that for D2. The diagonals are perpendicular. They have 90-degree angles between them, and the area once again is like in a rhombus, half into the length of diagonal 1 into the length of diagonal 2. And finally, let's look at the isosceles trapezium. So it has one pair of parallel sides, A and B. It has these top angles are equal, these bottom angles are equal. So this is equal to this and that is equal to that. One pair of sides are congruent, so this side and this side are equal in length. Their diagonals are congruent, they are equal in length. And the area is half into the sum of the parallel sides into the perpendicular height. Let's dive into questions. So if we had to find z, your first thing would be to make additional notes into the diagram. So you'll realize, so we know that one of these properties of an isosceles trapezium is that the bottom angles are equal, so this is also 63, and the top angles are also equal, so this means this is also a z. Now once we have this realization, the rest is easy. We know that this is a quadrilateral, so the interior angles add up to 360 degrees, which means 63 plus 63 plus 2z is 360. That gives us z is equal to 117 degrees, and the question is solved. Another kind of question they might give you is two rectangles, these being the dimensions and this being the area, and they might ask you to find the area of the second rectangle, right? So how you would approach this question is, you know that the area of a rectangle is length into width. So therefore, this area, which is 52, is equal to x minus 4 into x plus 5. We then turn it into a quadratic equation. We rearrange it, we'll get this. Then we factorize it, we get x plus 9 and into x minus 8. Factorization is covered in the video when we talk about quadratic equations. So if you do not know how to factorize, please do watch that video. Over here, you might be wondering why we're not taking minus 9 as a legitimate answer. The reason for this is that the length always has to be positive, so we only take the positive solution. Therefore, we can confidently say that x is 8 and not minus 9. Given that, we can find the side length. So we know that this is 8, so 2 into 8 is 16 plus 1 17, and the width is 8 minus 2, which is 6. Therefore, the area is 17 into 6, which is 102, and the question therefore is solved. Now let's look at circles, which is the second segment of this video. There isn't much emphasis on circle theorems in the SAT, so that's not something I'm listing out in theory. I'm just jumping into questions, and these will cover almost everything you do need to know about circles within the SAT, right? The area of a circle is 64 pi. What is the area of the square inscribed, right? So in this question, you might first think, hey, they've given us nothing, like what are we supposed to do with the area? So at this point, you need to just get creative, right? So what is the formula for the area of a circle again? It's pi r square. So we know pi r square is equal to 64 pi. From that, we cancel pi on both sides. We see that we get an expression r square is equal to 64. This means that r is 8. Therefore, we have found the radius. Now, the radius is a useful piece of information, but once again, initially you might be thinking the radius does not really give us anything, right? So at this point, we might want to construct a diagonal at this point. So what we notice is this diagonal is running through the center of the circle, right? And this kind of intuition comes to you with practice, so do not worry if you do not think about that, okay, you can draw a diagonal and therefore the question solution becomes evident. But it will become evident to you the more you practice. Anyway, so the diagonal runs through the center of the circle. Now a chord that runs through the center of the circle is the diameter. So that means the diameter is equal to the diagonal. Now the diameter is equal to 2 times radius, which is 16. Therefore, we have found the diagonal of the square to be 16 in length. Earlier, in one of my older videos, I did say that, in one of my previous videos, I did say that the diagonal is equal to the side length times root 2. So 16 is equal to side length times root 2. Therefore, the side length of the square is 8 root 2. Now that we have the side length, we can easily find the area of the square, which is 128. In this laws again, 8 square is 64, root 2 square is 2, 64 into 2 is 128. So initially, even though the question looked like we had nothing to solve it with, it was pretty easy to do. I do hope you're pausing the video, attempting these questions yourself, and then resuming it once you are confident you have found a solution, or you do want to just see the solution so you know how to approach it next time. So in another very common question they might ask is something along the lines of find the area of the shaded bit, right? So something you will need to understand for these kind of questions is that the shaded bit is nothing but the area of this sector minus the area of the triangle. We know the area of a sector is theta by 360 into pi r square, theta being the angle which we have to be 60 over here. Now, therefore, the area of the sector is 60 into 360 into 18 square, which is 324, into pi. That gives us 54 pi at the end. Therefore, we can substitute that over there and just write 54 pi down. Next, we need to find the area of the triangle. Now, we know if this this was the radius of the circle and this is also radius of the circle. So, if this was 18, this had to be 18. Therefore, we do know that this is an isosceles triangle at very least. Therefore, this angle and this angle would have to be equal. 180 minus 60 is 120. 120 divided by 2 is 60. Therefore, we get both these angles are also 60. Now we do realize that this is actually an equilateral triangle. This means this is 18 centimeters. All three sides are 18 centimeters. Once we have that, there are two ways we can find the area of the triangle. Either you can drop down a perpendicular altitude over here and then do your base into height and find the area of the triangle, or there is a formula for the area of an equilateral triangle if you have the side length. It is root 3 by 4 a square. So a square is 324. So the 324 root 3 by 4, that is 81 root 3. We can substitute it over there, and therefore that is the area of the shaded bit. Final question we're looking at for circles is this. So O is the center of the circle. OB is 5 centimeters. BX is 3 centimeters. Find the area of a circle, right? Now, it is always better that you label the information you have into the diagram. So I've put 5 there, I've put 3 there. Now, BX, O is one realization you should come up with is that BXO is a right angle. And this is because there is a circle theorem that says if you the radius and tangent always meet at 90-degree angles. So this is 90 and this is 90. Given that this is 90, Pythagoras theorem is applicable. Also, another thing you need to note is that OX is nothing but the radius of the circle. Therefore, we can find the radius of the circle using Pythagoras theorem. 5 square minus 3 squared, my bad, that is supposed to say 3. And therefore, that is 25 minus 9, which is 16. The root of 16 is 4, which is the radius of the circle. Now, area of the circle is nothing but pi r square, which is 16 pi, and therefore we have solved the question. We are now coming to the final segment of the video. I'm really proud of this table. And all of these images are in the public domain. It was hard finding them. Anyway, right, so... Right, the SAT does require you to know the volumes, surface areas of some 3D shapes. So let's start with the cube. That is what a cube is, and the surface area is 6a square. Why this is because there are 6 sides, all of which are squares. The area of one square is the side length multiplied by the side length, which is a square, and there are 6 of them, so it's 6a square. The volume is a cube, which is the volume. The cuboid, the surface area is 2 into LW plus LH plus WH. This is because there is one side that is LW. There are 2 sides that are of area LW. So therefore we have the 2 outside. There are similarly 2 sides of LH. It's that one and this one. And there are 2 sides with area WH, and therefore that's why the formula of the surface area is as it is. And the volume is length into width into height. Now, another thing they do want you to know is how to calculate the diagonal. So from this end to that end of the back, it is nothing but the length. The diagonal squared is the length squared plus the width squared plus the height squared. So it is like Pythagoras theorem, but in 3 dimensions, you could say. And once you get that sum, if you take the square root of it, you would find the length of the diagonal. So that's an additional fact you do need to know. The sphere is the surface area of this is 4 pi r square. The volume is 4 by 3 pi r cube. There is no way out but memorizing these. So I So you might want to take a screenshot of this table, print it out and learn it or something if you already do not know it. Now, before I come to this column, I want to clarify the difference between a prism and a pyramid, right? Now a prism will have a constant cross-sectional area throughout. So if I cut this over here, or if I cut this over here, the cross-sectional area is always going to be a triangle. Therefore, it is a prism. Similarly, the cylinder is a special type of prism. If I cut it here, we are still going to have a circle on the top. The cross-sectional area is constant throughout, right? Therefore, the cylinder is also a prism. But in a pyramid, the cross-sectional area rapidly decreases and terminates in an apex. So if I cut it over here, the square I will see over here is going to be smaller than the one on the base, and it does end in an apex. Similarly, if I cut it over here, the circle I'm going to see is going to be smaller than the one on the base, and it does end in an apex. Therefore, that is a pyramid. So is the cuboid a pyramid or a prism? If you thought prism, you are correct, because if I cut it over here, if I cut it over here, if I cut it over here, I'm still going to have a constant cross-sectional area of WH, right? Now with the distinction clear in mind, let's go to how do you find the volume of a prism, right? It is always the area of the base. So if it is a triangle multiplied by the height. We can see the cuboid is actually nothing different. We're multiplying the area of the base into the length over here, which you could think of as the height, because really it's just about orientation on how we label length, width and height, right? Similarly, for any prism, it is just the area of the base multiplied by the height. The cylinder is a special kind of prism. If you look at the volume, it is pi r square h, and this formula comes from the fact because it is a prism. We are looking at area of base, which is pi r square, into height, and therefore that is the volume. The curved surface area is nothing but 2 pi r, which is the circumference of the circle, multiplied by the height. The entire surface area is the curved surface area plus the surface area of these circles. So that's 2 pi r h, which is curved surface area, plus 2 pi r squared, because there are two circles to account for. When we look at a pyramid, the volume of a pyramid is 1 by 3 into the area of the base into height, right? And that is how we get the volume of a cone as well. 1 by 3 into area of the base, which is pi r squared, into height, yeah? And once again, you do need to memorize this. We're going to go through like 2 questions before we close this video. And so one common question they might ask is a cylinder or any random shape, in this case it's a cylinder, has a height of 10 centimeters and a radius of 5 centimeters. So that is melted to produce spherical balls of radius 1 centimeter. So they'll ask you how many of these balls can be made. Now the first thing is to figure out the amount of melted material you can produce. So that is pi, that is the volume of this cylinder, that is pi r squared into h. Okay, yikes, I substituted the things for this question wrongly. The radius is, so let's just assume, that the radius is 10 centimeters and the height is 5 centimeters, apologies. And therefore we will get the volume of the material to be 500 pi. Now the volume of a sphere is 4 by 3 into pi r cubed. 1 cubed is 1, so that stays as 1, so it is 4 by 3 pi. Now if we were to find the number of balls that we could make with height 5 centimeters and radius 10 centimeters, that would be 375 balls. What we would do is we would divide 500 pi by 4 by 3 pi. The pi's would cancel. 500 divided by 4 by 3 is the same as multiplying it by 3 by 4, which is 375. Apologies, this is supposed to be radius in the question and this is supposed to be height, my bad. So just to quickly give you the answer, if you had solved it according to what this question said, you would get 25 250 pi divided by 4 by 3, so 250 divided by about 4 by 3, that is 18.75, so you would get 187.5 balls. Could be made if we had height 10 and radius 5 instead of radius 5 and height 10, instead of radius 10 and height 5. Finally, another last question for this video is, If there is a 2 meter pipe that needs to be replaced, it is 0.1 meter wide with a 0.05 meter wide hole, what is the volume of material needed, right? So the first thing you need to find is the volume of the entire pipe. So that is pi r square h. So pi r square h is 2 meters, that's 0.02 pi. Then you want to find the volume of the hole. So that is pi into 0.025 into 0.0025 into 2. So that is 0.005 pi. Then to find the volume of material needed, you just find the difference between both, that is 0.015 pi, and therefore that is the volume of material we need to make the pipe in meter cube, obviously, over here. With that, in the next video we're going to look at coordinate geometry and functions. I do expect it to be another really long video, and with that, guys, have a great day. Thank you so much. See ya.